Thank you very much. I hope you can hear me okay. Don't worry, this is a short one before lunch. So the company I work for, Atkins, an engineering consultancy, one of the things we do is the seismic assessments for the cores of the UK's nuclear reactors. And what I'm going to talk about today is a Python-based toolset that we've developed to help us do that. But first of all, I need to explain a tiny bit about the UK's nuclear power stations, which are these advanced gas-cooled reactor stations. So the central core of them is made up of a large number of these graphite bricks that you can see here from this photo during construction. Each of these bricks is kind of about this size maybe, and there's thousands of those in the core. The UK doesn't normally get severe seismic events or earthquakes, or hopefully, but the regulator still requires that the people who operate these stations demonstrate that if they were to get one of these sort of 1 in 10,000 year earthquakes, they can shut it down safely. And the way that they shut them down is there's control rods that drop into channels within the core, within these bricks. So in order to prove that, you have to be able to assess the motion of the core during the earthquake, and it turns out that is a really hard problem to do. And in fact, I'd quite like to talk to the LMGC 90 guys if they're here, the guys who put that thing up outside. But basically, all we need to know for the sort of purposes of this thing today is that we've got what is quite a complicated finite element model, which runs in a commercial solver called LS-DYNA. And we can put a variety of sort of seismic motions, earthquake motions into this model, and then LS-DYNA runs the solution, and it gives us 120, 140 gigabytes worth of binary data that tells us the positions and velocities of the bricks in the core during the earthquake. But to some extent, that's not kind of that directly helpful to us, because what we really want to know is, how straight are those channels in the core? Are we still cooling the fuel efficiently? Are the keys that connect those bricks together, are they still intact? It's a sort of high-level questions, really. So there's quite a complicated set of post-processing calculations carried out to derive these sort of seismic assessment parameters from the raw data. And the existing toolset we had was based on Excel. I'll see if there's some groans. And it used VBA to handle the binary data and to carry out the actual calculations as well. And I think the phrase technical debt will probably be familiar to this audience. It had grown over time. I mean, this work was started quite a long time ago. As the models get more complex, there's new post-process requirements, stuff gets added in. It's kind of the way it goes. But to be honest, it was looking like for our new set of models, it was going to be very hard to put the new functionality we needed in and to be able to guarantee that, in fact, we weren't breaking existing functionality. So we didn't really want to start again from scratch, to be honest, because there's a lot of investment in this thing. But when we looked at our requirements, we sort of reluctantly came around to the idea that actually maybe that was what we needed to do. So we wanted something that was much more modular so that we could maintain it and we could extend it in the future. We wanted to have better plotting than we got in Excel, especially for sort of contour-type plots that it doesn't really do very well. And we had to have a high-level language to describe the actual calculations in, because they would be implemented by seismic engineers. They're not trained programmers or even necessarily people who have kind of grown up sort of using programming languages in that way. We wanted something a bit faster. I mean, the VBA-based one was taking sort of 4 to 6 hours to run a post-processing solution, which is a bit inconvenient. It's not too bad. And ideally, we wanted something that was cross-platform, because we were migrating the analysis from a Windows-based solution to sort of Linux servers as well. So this is what we came up with. It's a sort of 3-part architecture. We've got this kind of core program we call Aftershock, which is written in C++. It's got an embedded Python interpreter. And its job is to kind of take the whole stack of binary files that come out of LS-DYNA and sort of read through them in the right order, translate them, and so on. And then it's got a simple Python API that allows calculation scripts written in Python to actually access that data in a convenient fashion without the people writing the scripts actually having to understand the slightly horrendous and undocumented sort of format of these files. So the calculation scripts, we pick the scripts we want to run depending on what we're looking for, depending on the model we're running. They make pretty heavy use of NumPy for efficient element-wise operations. And I mean, output to tables is pretty trivial. That's just CSV format or something like that. We also wanted to do quite a lot of output to plots as well. And we ended up implementing our own sort of custom plotting package called Afterplot, which is based on matplotlib. And I'm sort of a bit less worried about this now that I've seen a lot of other people are developing their own plotting packages as well. So maybe this will make a lot of sense to you. But I think it's still worth looking at some of the reasons for that. Matplotlib is massively flexible, but that does kind of come with its own sort of complexity in terms of the API. And we didn't really think our client would want to pay for our Seismic engineers to learn how to use the Matplotlib API, to be honest. It enables us to enforce best practice. So there's some really simple things like you will have grid lines on your plots because they are turned on and you can't turn them off because that is actually appropriate for our types of plots. There's some more subtle things as well, like we've got our own custom color bar that's based on some quite comprehensive research we found that's supposed to improve the visualization compared to the sort of default color bars you get, things like that. It also enables us to make quite a strong demarcation between what you can change and what you can't change. So, you know, we can allow the user to alter, say, the axis limits, because you might need to do that to explain your data better, and they can do that either through a GUI or through an API on the plotting modules themselves. But we can prevent the user from modifying the actual data that's presented, or the stuff that really defines that data, so say like the axis labels or the units that are put on there as well. And that's not a security thing or about sort of malicious manipulation of data. It's really, as part of our quality control process, we want to be able to say, well, this has come out of a plotter that, out of a calculation script that we have demonstrated is correct. Therefore, we don't have to worry about the fact that actually it doesn't look exactly like the original sort of run of this post-processor, because we know that all they can have changed is the things we've allowed them to change. And the plotter also goes through the stack a bit and pulls out some information on which scripts and the versions of the scripts that have been used to produce the plots. I think, you know, reproducibility of data is a big thing in the scientific community at the moment, and I think it's a similar issue for us, to be honest. And the final bit of functionality was what I call store and restore. So you can produce PNG outputs or any sort of variety of a static image from Matplotlib. But once you've closed the figure window, the only way to get that back is to rerun the entire script. And it's not very elegant, and it's not really what we want to do with a sort of complicated post-processor like this. So we leveraged or sort of stole the way that Pickle internally deals with user-defined classes to provide something where we can save a plotter to disk, and then we can restore it complete with its GUI if people need to make minor changes. Alternatively, you can restore it in a script, and then you can sort of do batch operations. So say if you wanted to change all of your line thicknesses or something like that, you can do that. It's a simple change. And I think it's really impressive because in terms of the functionality that Python provides, because actually the sort of proof of concept script for that is probably only about 20 lines of code or something like that. And I think that's a real tribute to the sort of power you get from using Python and the sort of scientific packages that go with it. So overall, I think the results of swapping to the Python scientific stack have been strongly positive. We've got the modularity we wanted. We've got a reusable core that will save us a lot of time in the future. We got the better performance we wanted, and not having to deal with VBA's sort of array notation is a big improvement. Again, I think it's quite impressive, not from us, but for the developers who came up with this stuff, that actually the calculation scripts and the plotting library all ran cross-platform when we moved over to Linux with basically no changes at all. There was a bit more work with the embedded interpreter though, but you know, again, that saved us a lot of time. Just in terms of the challenges, I think a lot of it is, you know, if you're using engineers to write this kind of code, they're not necessarily used to writing performance-critical code, and you know, they can pick up simple, so functional Python and simple object-oriented Python quite fast, but element-wise programming is maybe a bit of a more difficult thing to get your head around, at least in terms of doing it in an efficient and a kind of an easily understandable way. But I think what is interesting is a lot of things coming up in the pipeline that will be really useful for us. So I think the embedded interpreter support is much better than Python 3. I think the successors to NumPy, Blaze, is going to provide things like sparse arrays and labeled arrays, better support for those features, which will be very good for us. And again, it looks like the next couple of versions of Matplotlib are going to provide a real step forward in terms of the API and probably the documentation for it as well. So a big thank you to all the people who are coming up with that stuff, really, because we're sitting right on the top of a lot of very hard work from other people. That's it, really. Thank you very much for listening.
Thanks for your talk. I'm wondering, what is your reason for using an embedding the interpreter as opposed to extending it or using an external library for doing the C work?
Yeah, it's a good question and not one I'm sure I've got a particularly good answer to. The co-author on the paper is actually the guy who came up with that part of it. I would have liked to see it done as an external library, I have to say, and to try, essentially having Python as the core and just calling an extension library to try that. It may have partly been familiarity, with the approach, I think, to some extent. But I mean, they're pretty symmetrical in Python, I think. So.
We have done it one way, not very difficult to do
yeah.
the other way. So.
Yeah.
Hi, great talk. I can see why you moved away from Excel with 120 gigs of data. First, a comment. It looks, you're already looking at Blaze. I don't know if there's anyone from Continuum here, but it may be that Blazer's direction has changed quite recently. But it looks like you could make good use of lazy loading and lazy evaluation element-wise. So there's a talk later on by Patrick on Biggest, which might be of interest to you.
Okay. Yeah.
My question, finally, is Matplotlib since 1.3 has pickling support. So what format are you using? Can you give us some more details about the store restore?
When we started this, Matplotlib didn't support that, and there was a thing called Ghost, I think, which was sort of an experimental implementation of pickling Matplotlib figures, because there's some stuff sort of in the object hierarchy that wasn't pickleable at the time. And I tried to get my head around the way Ghost did it, and I was a bit confused, to be honest. So the way we do it is really simple, and like I said, it's the same way as pickles your user-defined classes. All it does is the plotters are actually defined as a custom class, and the user creates an instance of that class. So what we have is when that instance is created, we actually store the parameters passed to it onto the instance that's created using the new method of a base class. And then when we store it, all we do is we pickle those parameters, because they are all pickleable. They're things like NumPy arrays or strings, describing a title, or just Python sort of objects. So it is, like I said, it's really simple. Yeah, but I mean, there's a couple of wriggles, things like you have to be able to handle whether stuff's being passed as keywords or positional parameters, and making sure that you're actually pickling the NumPy arrays in sort of an efficient format. But yeah, it seems to work really well.
Okay, thanks again.